Good morning, good evening, wherever you are. So for me, it's evening. And yes, I hear a slight skepticism in the voice of Steve regarding the quantum many-body states. And this is kind of what I expected. This is something that is probably quite unfamiliar for you. By the way, the camera is here, but my slides are here, so I will probably not look at you. Don't take that as offensive or so. Yes, so we need to do a bit of background work for this to be useful for you. So there's one part that I want to talk about. This is how does this came to be that we did something quantum and something neuromorphic. But I also want you to understand what quantum means and what neuromorphic means. So these are kind of our three things that we need for ingredients. And then at the and hopefully the 12-minute mark or so, we will come to the results. And then in the end, I really want to make an argument for why this kind of interdisciplinary and chancy work is something that we should all work on. And yes, so let's start. How this came to be, it's hard to talk about any project on brain scales without mentioning Karl-Heinz Meyer. The late Karl-Heinz Meyer, so he died in 2018. But we started working on this back in my master thesis, which was in 2016. And we started working with a group of Thomas Kasenza. And the idea was basically, we are all at the same institute and we are all physicists. So we are all people who think we can do everything in the world. And the idea was a bit that maybe what Thomas people want to do, so representing quantum many-body states, which I will explain in a moment what that is, could those people use the hardware that Karl-Heinz Meyer's people were building? And this was kind of the starting point, where we started the discussion. And on the side from Thomas, initially it was mostly Stephanie. And well, we spent the first year or so simply evening our language so that we could actually understand to each other. And of course, it wasn't a year full time. Everyone had its own project. So Stephanie was also a PhD student, just as me, starting to getting into my PhD at that time. So we also had our own projects to work at, but we kept at it. And after a time, we understood it, or we understood each other. And when Stephanie graduated, she had half a year or 3/4 of a year of a postdoc still at the Kirchhoff Institute. And that was the time where we also had enough hardware available. So basically, we decided, or she decided, she wanted to do this with her time. And then Robert took over. He's a master student of Martin Gärtner, and Martin Gärtner is the PI that joined Qbit in, I think, 2019, and he basically took over leadership in the project. But we also need kind of the theory behind it. This is what was introduced by Mihai Petrovic back in 2016 in his paper, and basically the Neuroteam A group from him in Heidelberg since that time somehow uses and tries to better understand LIF sampling, so sampling with LIF neurons, and this is kind of my personal background. But also, this is nice, this is neuromorphic, so we would like to use neuromorphic hardware. And since this is analog neuromorphic hardware, so this is the BrainScales ASIC on the left, and on the right, it's the system with an actual membrane trace on oscilloscope. And yes, this analog system is quite finicky to work with, so we also needed quite a lot of support from the electron equations group. And yeah, so with kind of this background set, and it really took some time to get us into the position to start, and also get me up onto my speed with Qbit Systems. We can come to the what is actually a Qbit system. Well, you probably know what a classical system is, so it can either be a 0 or 1. But a Qbit system is kind of more complicated. So there's also the way that they could be in a superposition of 0 and 1, and then you visualize this as this kind of Bloch sphere. And conceptually, it's a bit more complicated, but for the moment, we can just think of a point on the surface of the Bloch sphere. And this is essentially a complex superposition of the upstate up here, which is annoyingly in this image called 0, and the down state, which is annoyingly called 1. And we will later call it up and down. But this is kind of the typical way you can do spins. But the general state is not, so we cannot only have 0 and 1 or up and down, but rather we can have a complex superposition. So you can think about this as kind of vector space of linear algebra. You have two basis vectors. This is up and this down thing down here, and don't worry about the notation. Just think of these basically half angular brackets as a vector notation. So this is the basis state here. And then it has a complex coefficient up front here. And this is what we call, the wave function coefficient. And in total, this is the wave function in the end. And the problem now comes if we don't want to only talk about one spin, but about 2 or 3 or 4. Because then we need to have a coefficient for each of the basis functions. So we need a coefficient for the up, down, up component, but we also need one for the down, 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 or the up, up, up component. And this means for a larger system, we need exponentially many complex numbers. And something that scales exponentially is typically something that is rather bad, and you are typically not able to like it. So the task of the people that want to better understand quantum many-body systems, or the first task of that, is find an efficient description of that. Well, it turns out that in general, we have this kind of complex superposition for a wave function. So we have our basis functions down here, which I denoted phi, and they are the combination, all the possible combinations of ups and downs. And we have our complex coefficient up front here. But we are not really interested, or typically at least, we are not really interested in the exact representation, but rather we are only interested in what does the system represent, because we can only interact with this system in what quantum mechanics calls a measurement. So we are only really interested in measurement outcomes. And conceptually, you can think about it, asking the questions, if I have this kind of superposed qubit state down here, where the spin essentially points in the orthogonal direction towards the measurement axis. So I have a measurement along the z-axis up here, and my spin point in the orthogonal direction. That means at the measurement point, it needs to be projected onto the z-axis. So it can either be up or down if I'm looking at it and asking my system, what is your magnetization in the z direction? And in that case, it means in 50% of the cases, it will be up, and in 50% of the cases, it will be down. And now we can ask the question, what is the mean magnetization of any given state? So the mean magnetization is typically denoted by an M. And then you have the state that you have, that your system is in. And you have a measurement operator which you apply this on. And in order to get a scalar back out, you also have to multiply it with the complex conjugate of the state. But in the end, this ends up being a sum over all the basis states, well, the combination of all possible basis states, and the complex coefficients of those numbers. And if you know a bit about classical probability theory, then this kind of looks like an expectation value. So you have up here in the end, you have some kind of value that is based on the state of the system, so the phi prime and the phi, and you have a prefactor up front here. And yeah, okay, the prefactor at the moment is complex, but in principle, this is just an expectation value from a probabilistic point of view. So we have possible states X of our system, we have some assigned value to each state X, and we have a frequency which with the state appears, which we denote by P of X, and that is just a probability distribution in the end. And for certain type of quantum states, this can, so all possible measurements can be expressed as a probabilistic expectation value. So in order to get this kind of measurement operator down here, we need to find the corresponding function applied on an abstract state space, and we need to translate these kind of coefficients down here into the probability distribution. But once we have that, this is really just calculating expectation values. Again, I'm skipping over quite a number of complications, but for our understanding here, it's totally sufficient. Okay, what have we learned so far? Quantum many-body states require exponentially many complex numbers to be represented. Some quantum many-body states we can translate into a probability distribution, P of x. All expectation values from the quantum state that we may be interested in can then be calculated from the P of x. And now comes the big assumption, because if we have that translation from the coefficients to the probability distributions and from the measurement operator to the function, then we just need to sample P of x. And the nice thing is, if you cooperate with people who actually know the left-hand side, you only have to solve the right-hand side. And that is what we actually know how to do. So let me quickly run you through the neuromorphic sampling thing. That is what Mihai introduced back in 2016. And from our worldview, the brain is a network of networks of LRF neurons, but the LRF neurons is kind of an incidental part. It's just the model that we can easily simulate and that we can easily deal with. And from the perspective of this small network that we are interested in, and for example want to use to represent quantum many-body states, all the other networks, they are just appearing as noise input. And in the end, then we have a single neuron that is subject to a lot of background input that we implement as Poisson sources. And then we are interested in how does this neuron react to some input, because the rest of the network that we are actually interested in, that is still influencing our network. But we can think about this as just some external current of the system. And this Poisson input basically produces a free membrane potential distribution that the external current then shifts around. And if you shift the membrane potential over the threshold, then the firing probability of the neuron, or the firing rate of the neuron, that increases over time. And we can fit this activation function down here with the logistic function. And we can also think about this logistic function up here as calculating the probability of the neuron to be in the state 1. And we will come to how we assign the state 1 in a moment. It turns out that this activation function down here, that corresponds to sampling from a Boltzmann distribution. And at that point, we have a description for our, well, before I called it P of x, and here I call it P of z, but we have some probability distribution that we can form and that we can manipulate and that we can use our network to sample from. So last ingredient is how do we assign the states? And if you have these kind of neurons under Poisson input, then the membrane potential essentially performs a random walk. And at some point in time, the neuron spikes. And if the neuron has spiked, then it communicated something to all the other neurons. So we call it in the refractory state to be in the state 1, and otherwise we call it to be in the state 0. And then we can just look at when have neurons spiked, and based on that, assign them a binary state 0 or 1. And then we have this kind of temporal evolution that forms a sample from our probability distribution. Okay, 12 minutes. That's actually good. So, neuromorphic sampling. Well, we still need some neurons. The neurons that we get are from the BrainScales 2 ASIC. Again, we have some neurons up here, we have some synapses around, but basically we configure those to be in a hierarchical network where we have 2 layers. The visible layer is used to actually represent the probability distribution that we are interested in. The hidden layer is used to form the probability distribution over the visible layer. And then we can sample that network iteratively. Based on the samples, we can calculate gradients on the controlling host computer and write back the gradient applied to the parameters, and thereby optimizing the network the state that the network represents. And it turns out we can get, or at least now we can get up to 30 Hertz experiment rate, which makes this training kind of efficient. Okay, with that we have all the background collected. Let's come to the results. The first thing that we did was also the most challenging thing that you could come up, or at least it turned out that it is the most challenging thing. It's the classical Bell measurement. And if you have ever heard about the fundamental experiment that proof that nature is fundamentally quantum, that is this Bell experiment. The idea is that you have a source of photons that generates a pair of entangled photons that are measured at two different sites, which are far away from each other, so that the two sites cannot communicate in time with each other. And then you measure correlations between what party 1 measures and what party 2 measures. And it turns out that this correlation measure that we have down here, that if the world were to be purely classical, that would be bounded by being of magnitude smaller than 2. And then you can write down this the mathematical description for this entangled photon system, and it turns out this is also a 2-spin system, or the description of those is equivalent to the 2-spin system, and this is the particular Bell state that we implemented. And then we can perform this kind of measurement of the Bell observable that we have based on that state that we implemented. And then you see the violation of the classical bound. So what you see here in the inset, this is the actual training procedure. So we train our state, or our network, to represent a state that is denoted by these red dots here. And we see that we converge relatively quickly. So after a couple of hundred epochs, to more or less accurately predict the Bell observable. But it could also be that we only train the network to represent the Bell observable. And in order to kind of avoid that criticism, we then, after we have trained the system, we evaluate it at different angles. So basically different choices of the measurement. And this is what you see on the x-axis. And surprise, surprise, mathematics actually work, and we actually implemented the state, and then we can, just by re-evaluating the sample that we generate, find different values of the Bell observable, because not at every configuration of the basis choices here you can actually observe violations of the classical bound. So all you really need to take away from here is it works, and we actually represent the quantum state and not just the observable that we have implemented. Then we did this for a couple of larger systems, and it turns out that this really quickly degrades. It's not completely clear why this happens. This is both because the ASIC at that time had very limited time that we could run an experiment continuously, and then we had to stop, and then we had to restart the experiment in order to generate more samples. So this is one problem that plays into this, but that was also the end of the time that Stephanie had at Heidelberg. And Robert concentrated on a different class of quantum states, the so-called stochastic quantum states. It's basically that the class of quantum states that can have can be described by real valued coefficients. And for these, we could go up to like 10 visible states, and we had a significantly improved time. And these two publications up here, so the 22 one is what we did with Stephanie. This is the work was actually done in 2020, and the one with Robert down here, this is still the archive version, which is now under review. And we got the results, or we got the reviews, I think, yesterday. So we are still in the answering phase, but the order in which they are given here is the order in which they were made, and not the timing or the year that is here. Okay. I have 2 minutes left. Nice. So why even bother? This is kind of my argument. Why should you do that? And well, the easy answer is it's fun. This is why all involved PhD and master students did it. It's not necessarily why the PIs did it, but you should do things that are fun, and working with different people with a different background, that is also interesting. But it also exposes you to a different way of thinking, and that also means there's an opportunity to learn something. From a practical point of view, it was a stress test for brain scales. So we served as a sounding board for the brain scales development, and gave them some opportunity, or also challenge, to improve. We learned something about theory, but in the end, the really interesting part is this is a physical computing system. This system does not care about the size that you configure it to run. The system has time constant that it just evolves in time, which means that independent of the size of the problem that we would be looking at, the computation time would always be flat 5 seconds. Depending on the simulation that we would run and depending on the computer that we would use, we would get different times on a computer, but we would always get a scaling with the size of the system. And this is kind of where we can get inherent parallelism from. And this is one of the reasons why I find, especially this kind of analog, physical, real-time computing, whatever you want to call it, very interesting and very fascinating. Okay, with that, let me show you again a couple of people. Again, Karl-Heinz Meyer, he is the one who started all this and who allowed us to pursue this fascinating, albeit somewhat weird research avenue. Stephanie is currently a postdoc in Canada, and she, I think, joins Waterloo in the summer semester as a professor. Martin is a PI here at Qbit. Johannes took over the group from Karl-Heinz and very much also supported this endeavor, and without him, and especially without Sebastian, we wouldn't have been able to run this kind of stuff. Without Mihai, I wouldn't be here. And yeah, also without the rest of the electronic visions group, we wouldn't have been able to use the hardware with that little effort that I had to put into it. With that, thank you for your attention, and I'm happy to answer any questions.